Next we discuss problem number 26. It says if 50 ml milliliter of a solution that contains 0.001 moles of Ag plus ions is combined with 50 moles of a 0.01 molar HCl solution, how many Ag plus ions will remain in the mixture given Ksp of AgCl is 1 times 10 to the minus 10. So, first we need to calculate moles of Cl minus present in 50 ml of 0.1 molar. Okay, so moles of chloride ion, Cl minus ion present in 50 ml of a 0.10 moles HCl is 0.1 times 50 by 1000, right? Okay, so we get 0.005 moles. So this number of moles coming from number of moles of Cl minus coming from HCl now, and we have another Ag plus ion, right? So Ag plus also we know, okay, number of moles. Okay, so let X be the moles of Ag and Ag plus ion remains in solution. So initially we had 0.00 moles of Ag plus ion. Out of this 0.001 moles of Ag plus ion, X is the mole number of moles of Ag plus ion remains in the solution. So how many moles are reacting? Okay, so moles of Ag plus ion reacting or precipitated will be 0.001 minus X. So we can consider this one as 0.001 when X is very small compared to 0.01. So this is the kind of approximation. Now moles of, since AgCl ionizes as Ag plus Cl minus. So number of moles of Ag plus, same number of moles of Cl minus will react, right? So how many number of moles of Ag plus ion is precipitated? 0.001. So 0.001 moles of Cl minus will be precipitated. Okay. So therefore the moles of the number of moles of Cl minus ion will be precipitated is 0.001 mole, right? Because Ag plus equals concentration of Ag plus equals to concentration of Cl minus here. So we had 0.005 moles of Cl minus. Out of that 0.001 moles of Cl minus will be precipitated. So the number of moles of Cl minus remaining So number of moles of Cl minus ion remains is 0.005 minus 0.001. So, you get 0.004, right. So, total volume, now we are adding 50 ml of solution, 50 ml solution, we are adding 50 ml of HCl. So, 50 ml of Ag plus solution and 50 ml of HCl solution. So, total solution, total volume of the solution, the total volume of the solution is after mixing, the total volume of solution after mixing total volume of solution after mixing of 50 ml Ag plus solution and 50 ml HCl solution is 50 plus 50. So, we get 100 ml. Therefore, the concentration of Cl minus, the concentration of Cl minus remains remain unreacted So, how many number of moles of Cl minus ion is present? 0.004 in 100 ml. Okay, so the molarity of the concentration, molarity of the Cl minus unreacted is 0.004 times 100 by 1000, right. So, this means number of molarity. Okay, so this is the concentration of Cl minus. So, the concentration of Cl minus unreacted is 0.04 moles, right. Now, concentration of Ag plus, again Ksp is Ksp of AgCl is concentration of Ag plus times concentration of Cl minus. So, concentration of Ag plus is Ksp by concentration of Cl minus. Now, what is the value of Ksp? Ksp value is given, right. So, 1 times 10 to the minus 10 and the concentration of Cl minus is 0. This is 0. Okay, this is your 10. This will be at this will be 1000 by 100. Okay, so you get this. So, you get 0.04. So, you get basically this will be your 2.5 times 10 to the minus 8, right. This is the concentration of Ag plus. Okay. So, moles of Ag plus remaining in (100 ml) solution will be 2.5 times 10 to the minus 8 times 100 by 1000. So, you get 2.5 times 10 to the minus 9. Okay, this is the number of moles. Next, we move to problem number 27. It says, what will be the final pH when 200 ml of an HCl solution, pH 2, is mixed with 300 ml of a NaOH solution, pH 12. So we need to calculate concentration of H plus and concentration of OH minus here. So pH of HCl is 2. So therefore we can write pH means minus log concentration of H plus is 2. So concentration of H plus will be 0.01 molar. Okay. Now moles of H plus ions present in 200 ml, because the volume is 200 ml here, volume of HCl, so 200 ml of an HCl solution will be 0.01 times 200 by 1000. So we get 2 times 10 to the minus 3. Again the pH of NaOH is given, again pH of NaOH is 12, means minus log concentration of H plus is 12. So concentration of H plus ion, so the concentration of H plus ion in NaOH solution is 10 to the minus 12. Therefore again Kw is 1 times 10 to the minus 14. Okay. So Kw means concentration of H plus times concentration of OH minus. We are considering 298 K at 298 K. So concentration of H plus times concentration of OH minus gives 1 times 10 to the minus 14, and concentration of H plus of NaOH is given. So concentration of OH minus is we can calculate is 1 times 10 to the minus 14 by concentration of H plus of NaOH solution. So 10 to the minus 4 minus 14 by 10 to the minus 12. So we get 10 to the minus 2. So this is the concentration of OH minus. Okay. Done. Now we need to calculate, okay, so number of moles of, so the number of moles of which minus ion present in 300 ml of NaOH will be 10 to the minus 2 times 300 by 1000. So you get 3 times 10 to the minus 3. Okay, so we get the concentration of H plus ion is of HCl is 2 times 10 to the minus 3, and here we get the number of moles of OH minus ion present is 3 times 10 to the minus 3. So this is higher than, concentration of or the number of moles of OH minus ion is higher than the number of moles of H plus ion present. Okay. Okay, so therefore 2 times 10 to the minus 3 moles of H plus ion will be neutralized by 2 times 10 to the minus 3 moles of OH minus ion, because for every OH H plus ion we need one OH minus ion, right? So these many number of moles of H plus ion, H 2 times 10 to the minus 3 requires 2 times 10 to the minus 3 moles of OH minus ion, right? So therefore the number of moles of OH minus ion left, and total volume of the solution is left in 300 plus 200 means 500 ml, right? Left in 500 ml solution. So we had 3 times 10 to the minus 3 number of moles of OH minus ion, and these many 2 times 10 to the minus 3 moles of OH minus ion is being utilized here. So the number of moles of OH minus ion left will be 3 times 10 to the minus 3 minus 2 times 10 to the minus 3. So we get 1 times 10 to the minus 3 in 500 ml. Okay. Therefore, molar concentration of OH minus ion will be 1 times 10 to the minus 3 in 500. So 1000 by 500. So we get 2 times 10 to the minus 3 molar. So this is the molar concentration of OH minus ion. Okay. So we can calculate POH. So the molar concentration means concentration of OH minus, that is your unreacted. Okay. Therefore POH, or therefore concentration of H plus ion is Kw by concentration of OH minus ion, and Kw is 1 times 10 to the minus 14, and concentration of OH minus is 2 times 10 to the minus 3. So we get 0.5 times 10 to the minus 11. This is the concentration of H plus ion. So the pH of the solution, because we need to do the pH of the solution, final solution. So pH of the final solution will be, pH is minus log concentration of H plus, so minus log 0.5 times 10 to the minus 11. So if we calculate this one, we get the value 11.302. So this is the pH of the final solution. Next we move to problem number 28. It says calculate the degree of hydrolysis and the pH of a 0.5 molar KCN solution at 25 degrees Celsius. Given Ka value is given. So KCN is a salt of strong base KOH and a weak acid HCN, right? Okay, so KCN is a salt of a strong base KOH, potassium hydroxide, and a weak base HCN, right? Hence Cn minus will be hydrolyzed. So Cn minus plus H2O gives HCN plus OH minus. So now KH is concentration of HCN times concentration of OH minus by concentration of Cn minus. So we can write C square alpha square by C times 1 minus alpha, where alpha is the degree of hydrolysis. Okay, so like here Cn minus plus H2O gives HCN plus OH minus. So, initial concentration is C. Initial concentration is C, and this is 0 and 0. There is no HCN and no OH minus. And at equilibrium, we get C1 minus alpha, we get C alpha and C alpha, where C is the initial concentration like before, and alpha is the degree of hydrolysis. So, this is the value of Kh. Okay. Now, if we substitute this, so we get basically, okay, so we are what we are doing now, like before, we are multiplying by H plus and dividing by HCN. Okay. So, what we are doing here, we just little bit manipulation we are doing here. So, H concentration of H plus times concentration of OH minus. This thing we discussed in the class, in the lecture. Okay, actual when we discussed the theory. Okay, by concentration of H plus, because we are multiplying with H plus, so this will get cancelled, and concentration of Cn minus is there, and we are this HCN whatever we had in the numerator, we are taking in the denominator. So, concentration of HCN is here. Okay, so we get basically so this numerator gives Kw and the denominator gives Ka. Okay. Now, value of Kw we know. Okay. So, basically we get C square alpha square by C times 1 minus alpha. This gives actually C alpha square by 1 minus alpha. Okay. And this gives 10 to the minus 14 by 7.2 times 10 to the minus 10 at 298 K. It is given at 298 K. At 298 K, the value of Kw is given, and is 1 times 10 to the minus 14, and the value of Ka is 7.2 times 10 to the minus 10. So, this one C alpha square and 1 minus alpha, actually we can neglect, because when alpha is very very small compared to 1, we can write 1 minus alpha is 1. Okay. So, this we can write 1 is get 1.39 times 10 to the minus 5. So, considering 1 minus alpha is to 1 when alpha is very very less than 1. So, we consider, that is why denominator we can write 1 here. So, we can get alpha is square root 1.39 10 to the minus 5 by C is 0.5. Now, we put the value of C 1.39 times 10 to the minus 5 by 0.5. So, if we do it, we get the value of alpha 5.27 times 10 to the minus 3 is the degree of hydrolysis. The first part is done. Okay, degree of hydrolysis is calculated. Now, we need to calculate pH of the solution. So, in order to calculate pH, we know the concentration of OH minus, right. So, concentration of OH minus here. So, concentration of OH minus is C alpha. Again, concentration of OH minus is C times alpha. C is 0.5 and the alpha is 5.27 times 10 to the minus 3. So, we get 2.635 times 10 to the minus 3 molar. Okay. So, concentration of H plus is Kw, because concentration of OH minus times concentration of H plus is Kw. So, concentration of H plus will be Kw by concentration of OH minus. Now, value of Kw at 298 K is 1 times 10 to the minus 14 by 2.635. Okay. So, if we calculate this one, so pH is minus log concentration of H plus. So, minus log 1 times 10 to the minus, okay, by 10 to the minus 3 is also is there. So, 1 times 10 to the minus 14 by 2.635 times 10 to the minus 3. So, if we calculate, we get the pH. So, pH is 11.42. So, this is the value of pH, and alpha we have already calculated. Alpha is 5.27 times 10 to the minus 3. So, the degree of hydrolysis alpha is 5.27 times 10 to the minus 3, and pH of the solution is 11.42. Next we move to problem number 29. It says when 10 cc of 0.2 normal NaOH is mixed with 30 cc of 0.1 normal CH3OH, calculate the pH of the resulting solution. Given Ka for acetic acid is 1.8 times 10 to the minus 5. The solution is 1000 cc of 1 normal of any solution contains 1 equivalent So, 10 cc, we have 10 cc of 0.2 normal NaOH. So, 10 cc of 0.2 normal NaOH contains 2 by 1000 equivalent of NaOH, and we have 30 cc of 0.1 normal CH3COH and 30 cc of 0.1 normal CH3COH contains 3 by 1000 equivalent of CH3COH. When they are mixed, so 2 by 1000 equivalent of NaOH is neutralized by two by 1000 equivalent of CH3OH to produce 2 by 1000 equivalent of salt, right. So, 2 by 1000 equivalent of base is neutralized by 2 by 1000 equivalent of acid. So, to produce 2 by 1000 equivalent of salt, right. So, we have here acid extra, right, and we are left with three by 1000 minus 2 by 1000 equals to 1 by 1000 equivalent of acid, right. So, we need to calculate the pH. So, we use now the Henderson equation. Okay. So, from Henderson's equation, you can write pH equals to pK plus log concentration of salt by concentration of acid. right. So, pH gives minus log value of K, pK is K value, well, minus log Ka. So, minus log 1.8 times 10 to the minus 5 plus log salt is 2 by 1000 and as concentration of acid is 1 by 1000. So, you get pH is minus log, you can write this one as Ka. So, minus log 1.8 times 10 to the minus 5 plus log 2. So, you get the value of pH is 5.04. Next we move to 30. Next we move to 30, problem number 30. It says the pH of a BaOH solution is 10.6. Determine its solubility and its solubility product. So, here pH is 10.6. So, we know pH plus pOH is 14, right. So, we get pOH is 14 minus pH. So, 14 minus 10.6. So, gives 3.4. Now, what is pH? pH is minus log concentration of OH minus. So, this gives 3.4. So, from there we calculate concentration of OH minus is 3.98 times 10 to the minus 4 moles per liter, moles per liter. So, this is the concentration of OH minus. Okay. Next, what we need to do? We need to consider how BOH2 is dissociated. Okay. So, BOH3 ionizes as BOH2 and ionizes as BOH2 ionizes as B2 plus 2 OH minus. So, it is clear that that 1 mole of BOH2 gives 2 moles of OH minus, right. 1 mole of BOH2 gives 2 moles of OH minus. Okay. The solubility, therefore, the solubility of B2 plus will be half times concentration of OH minus, will be half times 3.98 times 10 to the minus 4 moles per liter. So, we get roughly 2 times 10 to the or 1.99 rather 1.99 times 10 to the minus 4 moles per liter. So, now we can calculate KSP. Okay. So, the KSP, the solubility product of BOH2 So, concentration of B plus 2 plus times concentration of OH minus raised to the 2. So, concentration of B plus we know 1.99 times 10 to the minus 4 and concentration of OH minus we know 3.98. So, times 3.98 times 10 to the minus 4. So, if we calculate this one we get 3.15 times 10 to the minus 11. So, this is the solubility product of BOH